Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical specs to the most practical ones. So if this is the first video that you're watching or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present an introduction to epoxy adhesives. Adhesive is defined as a material which, when applied on substrate surfaces, can join them and resist their separation. Epoxy adhesives were introduced in early 1960s. They are capable of bonding different substrate materials, for example, metallic alloys, aluminum, wood, concrete, glass, ceramic, and other various substrates. An improved fatigue performance of the bond can be resulted using these systems by providing relatively uniform stress distribution in the joint. They can be formulated for certain requirements, and also the use of these adhesives can facilitate the fabrication of complex shapes. One of their advantages is that they are capable of being used for joining thin gauge metal substrate, for example, in honeycomb assemblies. Their other advantages include their high mechanical strength in terms of tensile and compressive, their thermal resistance, and substantial toughness. They also result in a low shrinkage and have a high adhesive strength. In addition, these systems are inert and exhibit a good dimensional stability. Epoxy adhesives are also resistant to a range of chemicals and climate conditions. Epoxy adhesives can be used in various industries, including aerospace, civil engineering, automotive, chemical, electrical, marine, leisure, etc. Epoxy-based adhesives are the most important structural adhesives. They combine both high load bearing and ease of processing. Other substantial properties of these systems include their versatility in terms of processing, properties, and cure. Moreover, they are able to operate in long-term application at relatively high temperatures. Epoxy adhesives also render all the advantages associated to other epoxy systems. For example, in their cure reactions, no volatile byproducts, for example, water is produced. For the adhesives, it is crucial as there is no need to apply high pressure during the bonding operations. Moreover, if applied on well-prepared surfaces, epoxy adhesives often exhibit good weathering properties and relatively low shrinkage during the cure. Because of the various types of epoxy resins, hardeners, additives, etc., a vast number of epoxy adhesive formulations exist. However, the most common epoxy type used in the formulation of these adhesives is the conventional diglycidyl ether bisphenol A resins. A large number of curing agents can be employed in this system. Other components often found in the adhesive formulations include accelerators, catalysts, viscosity modifiers, fillers, and additives such as toughening agents, wetting agents, etc. Epoxy structural adhesives are available in various forms, for example, liquid, paste, solid, film, or carrot film forms. Film adhesives are generally available in supported or unsupported forms. Supported film adhesives contain scream carrier, for example, nylon or polyester, and are relatively easy to handle as they offer more controlled regulation of bond thicknesses. Supported film adhesives are generally employed in relatively large area bonding applications. There are also times when epoxy adhesives are the best solution for joining two substrates, or even the only alternative. Outstanding advantages of epoxy adhesives include they provide a large stress-bearing area, they provide excellent fatigue strength, they can absorb shocks, they can be used to inhibit corrosion, and they can be used for various geometries with different thicknesses. However, for joining of two substrates, epoxy adhesives could be the worst possible option. Like other processes, the employment of adhesives for a joining task would have distinct disadvantages in specific applications. For example, the surface has to be cleaned for a good bonding. Some epoxy adhesives has long curing processes. Sometimes heat and pressure has to be applied, and their health issues have to be considered as well. Often a trade-off in performance, production capacity, cost, and reliability has to be considered before choosing adhesives for joining different substrates. Before describing epoxy-based adhesives, it is necessary to elaborate the two major theories associated to the adhesives: theories of adhesion and the wetting phenomena. Theories of adhesion discuss why do materials stick to another in the first place, and the wetting phenomenon, which is probably the most important factor in adhesion, talks about how and to what extent surfaces can be wet by the adhesives. Wetting influences the strength of an adhesive joint. The phenomenon of adhesion can be explained based on four main theories: mechanical interlocking, electrostatic, diffusion, and the adsorption theory. Mechanical interlocking suggests that the adhesion is primarily dependent upon the mechanical keying of the adhesives into substrate surface irregularities. In mechanical interlocking, the surface topology is quite important, and surface preparation plays a crucial role. The electrostatic theory of adhesion proposes that the adhesion is due to the existence of an electric double layer across the interface of the joints. Based on the diffusion theory, the adhesion between the adherent and the substrate is due to the intermixing of the two contact substrates at this molecular level. For this type of adhesion to happen, the mobility of the adhesive molecules as well as the compatibility of the adhesives and the substrate are essential. The diffusion mechanism is generally considered responsible for the self-adhesion or solvent adhesion in thermoplastics. Finally, adsorption theory, which is the most acceptable theory for the adhesive bonding with epoxies, considers sufficiently intimate intermolecular contact between the substrate and the adherent. Based on this theory, adhesion occurs because of surface force interactions, for example, van der Waals forces, permanent dipoles or hydrogen bonds, etc., between the atoms in the two contacting materials. The excellent adhesive properties of epoxy is often attributed to this mechanism, and that's because the presence of pendant hydroxyl groups which exist within the molecular structure of most epoxies. These pendant groups are capable of interacting, for example, via hydrogen bond formation with hydroxyl groups frequently found in abundance on the most surfaces. Primary covalent bonds can also occur during adhesion by the process of chemisorption. It should be mentioned that all intermolecular forces are very short-range and need proximity to act. Moreover, all substrates, even the most polished ones, are still exceedingly rough. Therefore, only a very small portion of the surface are in true intermolecular contact, unless the adhesive has the ability to flow and achieve contact with the majority of the substrate surface. This indicates the importance of wetting in achieving a good adhesion and a high load bearing capacity. Wetting, which is simply the ability of a liquid to wet a substrate surface, significantly influences the strength of an adhesive joint. It is quantified in terms of the contact angle, which is the angle liquid, here the adhesive droplets from when placed in contact with a solid surface. The contact angle can be related to the surface energies of the two contacting materials. A schematic of the contact angle has been presented here. Based on surface free energies, solid substrate surfaces can be categorized into low surface free energy solids, for example fluorinated and hydrocarbon polymers with a surface energy around 20 millijoule per square meter, Polymers with considerable polar characteristics and high surface free energy solids, for example, inorganic materials and metals with free energies of often more than 500 millijoule per square meter. Epoxy adhesive exhibit a surface energy of approximately 45 millijoule per square meter. This means that epoxy adhesives are not capable of wetting surfaces with relatively low energy surfaces such as polyethylene, whereas the reverse is expected with high surface energy solids, for example metals. It should be mentioned that the absorption of atmospheric contaminants and moisture can reduce the surface energy of metals and is detrimental for the adhesion process. This also indicates the need for the surface pretreatment before applying an adhesive. As the adhesion occurs within a few molecular layers of the contacting materials, substrate surface must be treated for efficient intermolecular interactions. The level of the desired strength, the expected longevity, the service environment, and the nature of the substrate determine the severity of the required surface preparation. The main surface treatment employed for adhesion processes are solvent cleaning, mechanical abrasion, and chemical treatment. The ultimate aim of all these methods is to increase the surface free energy of the substrate and promote adhesion wetting. In solvent cleaning, the aim is to remove organic contaminants, for example greases, oils, etc., from the surface. Sanding of the substrate surface with abrasive paper and grit blasting are of mechanical abrasion methods. Chemical pretreatment is the most important category for some substrates such as aluminum and titanium alloys often used in aerospace industries. The primary aim of chemical preparation of alloys are to remove the existing unstable oxide layer at the surface and to generate a new oxide layer conducive to both good adhesion and stability. There are several chemical treatments have been introduced for surface treatments of steel alloys, aluminum alloys, titanium alloys, or fiber reinforced composite, which are necessary to ensure good adhesion at their surfaces. Chemicals such as sulfuric acid and hydrofluoric acid can be used for steel alloys, whereas the surface treatment of aluminum alloys can be conducted through chromic sulfuric acid etching or through anodizing techniques. Alkaline hydrogen peroxide etching and a sodium hydroxide anodizing process can be employed for the surface treatment of titanium alloys. There is also the possibility of using primer to enhance the adhesion. Substrate surface primers are frequently employed for the adhesive bonding of many metallic alloys and other substrates. Primary roles of primer include protection, wetting enhancement, corrosion inhibition, and durability enhancements. Primers protect the freshly prepared metallic surfaces from atmospheric contaminants, for example water, hydrocarbon, etc. In this case, primers, which are often solvent-based systems, cover the surface with a layer that is highly compatible with the adhesive. This layer also reduces the level of the free energy of the surface, which in turn reduces the risk of contamination. Employing primers can also solve the potential wetting problems that might be associated with the use of certain adhesives. In addition, corrosion-inhibiting primers, which comprise of an epoxy and a strontium chromate in a solvent base, are often suggested with aluminum alloys following anodizing pretreatments. Finally, primers, in particular organosealant-based primers, may result in durability enhancements and interfacial stability in the presence of moisture. Epoxy zinc-rich primers have also been produced for corrosion inhibition in steel structure, which contain zinc dust as an active ingredient. These systems can be applied similar to other conventional primers. Okay, thanks for your attention. I hope you enjoyed the video. Please share your thoughts, comments, or questions, and I will come back to you soon. Thank you.